Current trend reversed. Scientists investigate the setback effect in electric current. Artistic impression of the experiment in which Hausler and colleagues first heat one of two quantum gas clouds and then connect them with a two-dimensional channel, such that they can equilibrate. When a piece of conducting material is heated up at one of its ends, a voltage difference can build up across the sample, which in turn can be converted into a current. This is the so-called setback effect, the cornerstone of thermoelectric effects. In particular, the effect provides a route to creating work out of a temperature difference. Such thermoelectric engines do not have any movable part and are therefore convenient power sources in various applications, including propelling NASA's Mars rover Perseverance. The setback effect is interesting for fundamental physics, too, as the magnitude and sign of the induced thermoelectric current is characteristic of the material and indicates how entropy and charge currents are coupled. Writing in Physical Review X, the group of Professor Tilman Esslinger at the Department of Physics of ETH Zurich now reports on the controlled reversal of such a current by changing the interaction strength among the constituents of a quantum simulator made of extremely cold atoms trapped in shaped laser fields. The capability to induce such a reversal means that the system can be turned from a thermoelectric engine into a cooler. Which way, please? The experiment, conducted by doctoral researcher Samuel Hausler and coworkers in the Esslingen group, starts with a cloud of fermionic lithium atoms that are cooled to temperatures low enough that quantum effects determine the behavior of the ensemble. The cloud is then separated into two independent halves of equal atom number. One of them is heated, before the two reservoirs are connected by a two-dimensional channel. The equilibrium state that thus develops is as expected. After a sufficiently long time, the two halves contain equal atom numbers at equal temperatures. More interesting is the transient behavior. During the equilibration process, the atom number in each reservoir changes, with the atoms ebbing and flowing between them. In which direction and with what amplitude this happens depends on the thermoelectric properties of the system. Thanks to the exquisite control over the system, the researchers were able to measure the transient behaviors for different interaction strengths and atomic densities inside the channel and compared them to a simple model. In contrast to solid-state systems, where most thermoelectric properties can be measured in simple, well-defined experiments, in these small clouds of atoms the parameters are inferred from fundamental quantities such as the atom density. Finding a procedure that properly extracts the thermoelectric quantities over a wide range of parameters was a key point of the work. The team found that the current direction results from a competition between two effects, see the figure. On the one hand, left, the thermodynamic properties of the reservoirs favor the increase of atom number in the hot reservoir, to equilibrate the chemical potentials of the two halves. On the other hand, right, the properties of the channel typically make the transport of hot, energetic particles easier, because they have a large number of possible pathways, or modes, available to them, leading to an increase of the atom number in the cold reservoir. Schematic of the two options how the atoms can reach thermal equilibrium starting from two reservoirs at different temperature. Credit. S. Hausler, ETH Zurich. A superfluid traffic regulator. With a non-interacting gas, it is possible to compute the dominating trend between the two competing effects once the precise shape of the atom cloud is known and taken into account. In the system of Hausler et al., this can be done very accurately. Both in the computation and in the measurements, the initial atom current flows from the hot to the cold reservoir and is stronger for low atomic densities in the channel. When the interactions are tuned up to the so-called unitary regime, the behavior of the system becomes considerably more difficult to predict. The computation becomes intractable without wide-ranging approximations, due to the strong correlations that build up in the gas. In this regime, the quantum simulation device of the ETH researchers showed that for high enough mean temperature and low atom density in the channel, the current also flows from the hot to the cold reservoir. However, it can be reversed when the channel density is increased using an attractive gate potential. Above a certain density threshold, the atoms in the channel undergo a phase transition where they form pairs showing superfluid behavior. This superfluid region in the channel limits the transport of unpaired, energetic particles, favoring the transport from the cold to the hot reservoir and hence the reversal of the thermoelectric current towards better thermoelectric materials thanks to interactions. Understanding the properties of matter through thermoelectric measurement improves the fundamental understanding of interacting quantum systems. Equally important is to identify new ways to design well-performing thermoelectric materials that could efficiently transform small heat differences into work or, if used in reverse mode, act as a cooling device, known as a Peltier cooler. The efficiency of a thermoelectric material is characterized by the thermoelectric figure of merit. Hausler et al. Have measured a strong enhancement of the value of this figure when cranking up the interactions. While this enhancement cannot be directly translated into material science, this excellent cooling capability could already be used to reach lower temperatures for atomic gases, which in turn might enable a broad range of novel fundamental experiments in quantum science. Latest thing switched. Scientists examine the setback impact in electric flow. Creative impression of the examination in which Hausler and Associates first warmed one of two quantum gas mists and afterward interface them with a two-dimensional channel, to such an extent that they can equilibrate. At the point when a piece of directing material is warmed up at one of its closures, a voltage distinction can develop across the example, which thusly can be changed over into a current. This is the supposed setback impact, the foundation of thermoelectric impacts. Specifically, the impact gives a course to making work out of a temperature contrast. Such thermoelectric motors don't have any mobile part and are accordingly advantageous force sources in different applications, including pushing NASA's Mars Wanderer Perseverance. The setback impact is intriguing for major physical science, as well as the greatness and indication of the initiated thermoelectric flow is normal for the material and shows how entropy and charge flows are coupled. Writing in Physical Review X, the gathering of Professor Tilman Esslinger at the Department of Physics of ETH Zurich presently writes about the controlled inversion of a particularly current by changing the association strength among the constituents of a quantum test system made of incredibly cool molecules caught in formed laser fields. The capacity to actuate such an inversion implies that the framework can be abandoned a thermoelectric motor into a cooler. What direction, please? The analysis, led by doctoral scientist Samuel Hausler and collaborators in the Esslinger bunch, begins with a haze of fermionic lithium iotas that are cooled to temperatures low sufficient that quantum impacts decide the conduct of the outfit. The cloud is then isolated into two free parts of equivalent particle number. One of them is warmed, before the two supplies are associated by a two-dimensional channel. The harmony expressed that along these lines creates as true to form. After an adequately lengthy timespan, the two parts contain equivalent iota numbers at equivalent temperatures. More intriguing is the transient conduct. During the equilibration cycle, the particle number in every supply changes, with the iotas ebbing and streaming between them. In which bearing and with what adequacy this happens relies upon the thermoelectric properties of the framework. On account of the wonderful power over the framework, the specialists had the option to quantify the transient practices for various connection qualities and nuclear densities inside the channel and contrasted them with a straightforward model. Rather than strong-state frameworks, where most thermoelectric properties can be estimated in straightforward, clear-cut investigations, in these little billows of iotas the boundaries are construed from basic amounts like the particle thickness. Discovering a system that appropriately extricates the thermoelectric amounts over a wide scope of boundaries was a central issue of the work. The group tracked down that the current-bearing outcomes from an opposition between two impacts, see the figure. From one viewpoint, left, the thermodynamic properties of the supplies favor the increment of molecule number in the hot repository, to equilibrate the compound possibilities of the two parts. Then again, right, the properties of the channel ordinarily make the vehicle of hot, vigorous particles simpler, in light of the fact that they have an enormous number of potential pathways, or modes, accessible to them, prompting an expansion of the molecule number in the cool repository. Schematic of the two alternatives: how the particles can arrive at warm balance beginning from two repositories at various temperature. Credit. S. Hausler, ed. Zurich. A superfluid traffic controller. With a non-cooperating gas, it is feasible to process the ruling pattern between the two contending impacts once the exact state of the molecule cloud is known and considered. In the arrangement of Hausler et al., this should be possible precisely. Both in the calculation and in the estimations, the underlying particle current streams from the hot to the cool repository and is more grounded for low nuclear densities in the channel. At the point when the collaborations are adjusted to the supposed unitary system, the conduct of the framework turns out to be impressively more hard to anticipate. The calculation gets immovable without wide-going approximations, because of the solid connections that development in the gas. In this system, the quantum reproduction gadget of the ETH analyst showed that for sufficiently high mean temperature and low iota thickness in the channel, the current likewise moves from the hot to the cool repository. Notwithstanding, it very well may be turned around when the channel thickness is expanded utilizing an alluring door potential. Over a specific thickness limit, the molecules in the channel go through a stage progress where they structure sets showing superfluid conduct. This superfluid locale in as far as possible the vehicle of unpaired, enthusiastic particles, preferring the vehicle from the cold to the hot repository and thus the inversion of the thermoelectric flow towards better thermoelectric materials on account of cooperations. Understanding the properties of issue through thermoelectric estimation improves the essential comprehension of connecting quantum frameworks. Similarly significant is to recognize better approaches to configuration well-performing thermoelectric materials that could productively change little warmth contrasts into work or, whenever utilized backward mode, go about as a cooling gadget, known as a Peltier cooler. The productivity of a thermoelectric material is described by the thermoelectric figure of legitimacy. Hausler et al. Have estimated a solid improvement of the worth of this figure while turning up the collaborations. While this improvement can't be straightforwardly converted into material science, this fantastic cooling ability could as of now be utilized to arrive at lower temperatures for nuclear gases, which thus may empower a wide scope of novel key analyses in quantum science.